In this video, we solve problem 14.2.028 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use an improper double integral to find the volume of the indicated solid, and it was in a picture for us, but they gave us z equal to this function, and they said that x and y both go to infinity. So all that's telling us is that we want the volume under this function in that first octant where x and y are both going to infinity, and at the same time as x and y go to infinity, z approaches 0. You can see that when x and y are both 0, z will be e to the 0, which is 1, and then as x and y increase, it's going to get farther and farther, or get closer and closer to 0. The integrand will. So we just want to evaluate this as a double integral, or excuse me, an improper integral inside an improper integral. That's going to represent the volume that we're looking for. And so I'm ignoring this one on the outside for a moment, and then I am rewriting that one on the inside. The upper limit is what makes it improper. So I'll take the limit as b goes to infinity of almost exactly the same integral. But instead of integrating from 0 to infinity, which makes it improper, we'll integrate from 0 to b. Now this is the limit of a proper integral in terms of y. So we can evaluate this using the fundamental theorem of calculus and then evaluate the result of that as we're going to evaluate the limit of the result of that, as b goes to infinity. Then we're just going to have a function of x here. And we're going to do the same thing on the outside. Now here, I've got a function nested inside another function. So u substitution makes the most sense for taking this antiderivative. I think I'll distribute that negative 1/3 to everything. So u is equal to this. Then du, if I'm treating y as my variable and x as a constant, is just negative 1/3 times dy. So if I want to get dy by itself, I'll just multiply both sides by -3. And now I have the integral from 0 to infinity of this. And if I want to write everything here in terms of u, this dy is -3 times du. This is e to the u by design. But we also need new bounds. Now these bounds are bounds for y. So in order to find the bounds for u, we need to substitute the bounds for y into this function. So we'll evaluate this at y equals b. And we'll evaluate the same expression at y equals 0. When y equals 0, we just get negative 1/3 x. And over here, if you want, you can factor out the negative 1/3 again. That's negative 1/3 times the quantity x plus b. So that's our new upper limit, and that's our new lower limit. The antiderivative of e to the u with respect to u is just e to the u. And there's still this dx on the outside. I'm not really doing anything with it. I'm just sort of bringing all of that down. And then we evaluate this from u equals negative x/3 to u equals negative 1/3 x plus b. And we've already integrated with respect to u, so that du is gone, and then this dx comes down. So all of this in brackets here is represented here, except I forgot to write that limit as b goes to infinity out front. So that's really important. It needs to be there. Okay, so this on the outside is doing nothing really for us. We're just sort of bringing it down just to keep everything equal to that volume that we're trying to find. When we evaluate this at this limit and subtract, we'll get this result. And I factored the -3 out because it's a constant. So we're going to have the limit as b goes to infinity of e to the -1/3 x plus b minus e to the negative x over 3. And this is as b goes to infinity. So if we're thinking of x as fixed temporarily, so x is a constant, as b goes to infinity, this is e to a really large negative power. So e to a really large negative power is very close to 0. And as b gets larger and larger, that fraction, because that's what it represents, there's going to be an e in the denominator, that's going to get smaller and smaller because that denominator is going to grow. So we'll have a 0 there. That goes to 0. And the limit of that constant is just the constant. So our integrand is this, the integral from 0 to infinity of -3 times that negative exponential. Negative times a negative is a positive. Some people will really have a hard time with me having that sign there. It just means +3 for right now. And then this is just a calculus 2 improper integral. So I've got an upper limit of infinity. So I will replace that upper limit with a b and take the limit of the result as b goes to infinity. Oh, and I forgot my 3. I'll bring my 3 out front there. Okay, well, that's e to the kx. The antiderivative of e to the kx is e to the kx. And then we have to divide by k. Dividing by k is the same as multiplying by multiplying by 1 over k. And if k is -1/3, 1 over k is -3. So that's our antiderivative, and then we evaluate that from 0 to b. Oops, I forgot to put my limit there. And then we're going to take the limit of the result as b goes to infinity. So this becomes -9 times the limit as b goes to infinity of this expression. Got e to the -b over 3 minus e to the 0. And as b goes to infinity, e to a really large power, large negative power, is going to approach 0. And then we have a -9 times a -1, which is a +9. So that's easy breezy. That's our answer, and that's the volume. I do want to show you one thing before we go. We're finding this volume here. Now, because x and y are going to infinity, you're not going to be able to see the whole thing. You could never sketch the whole thing because you have to imagine that x and y are both going out to infinity. But this is what our surface looks like. We're just finding the volume between that surface and the xy plane and that first octant. Turns out that that volume is equal to 9.